Now he's sick.
They had a whole frequently asked questions section. Like, how do I know I'm not going to get caught? They gave a real detailed answer.
With our state-of-the-art website, we make sure that your privacy is your privacy.
You don't pay until you have evidence.
With this 30-day free trial, and you let them go to court and get your money back.
I'm concerned with this guy behind me.
$5 a piece for heads.
You do not want a free trial on a site like that.
You can go eliminate anything you want for 30 days.
This is a one-time free offer.
Well, speaking of I guess free offer type stuff, in a much more normal conversation. So I listen to a lot of audiobooks, and so I've been a member of Audible.com since like 2004. So for a long time, right? Yeah, Amazon has owned them for a while. This is way before Amazon owned them, so I've been a member. So I have hundreds of books on there that I'm like a subscriber, so then you get books every month. Well, I happened to look on my my screen, like for my books in my library, and then I just happened to I saw when I started, and I kind of just did the math. Like, I'm like missing 81 books. There's 81 books more books that I should have than I do have. So I contacted them, like, and, because at the end of a month, any credits, you can only roll over 12 credits. So you get 2 credits per month, so they expect you to be using your credits. It's 1 book per credit. And so if you have more than 12 in your account at the end of the month, those drop off, so to make room for the new ones. So I thought I always spent my credits, but they said, "Oh well, some of those credits must have fallen off, so they're gonna give me 81 credits on my account," and I haven't until like May 16th to buy 81 audiobooks.
Awesome.
Huh? Well, I already have like my list of my next 30 that I'm like already in my library ready to read.
So you like look ahead?
I have to just go on there and buy all the books that I'm interested in.
I might read that.
Actually, I guess I have 83 books because I'll also have my 2 from. All right, so that's not us.
I don't know what needs space. Thank you,
Okay, so we wrote some logic last time to have this little deathmatch thing going on, right? Oh, can we hit the third button down over there, please? So we created an array that had a couple of, or a list that had a couple of players in it. We created our roller for initiative. We went ahead and rolled. Figured out who gets to go first. We toggled back and forth between those people. We give ourselves a d20 for our attack roller that rolls against the armor class. Then we said, while Mike and Blaine are both alive, we'll have the first guy. We figure out who the first guy is, and that's based on current player index. We have who the last guy is based on current player index +1. We have both of the people display themselves. Then we have the attack roller roll. Try to hit. So the first guy tries to hit last guy. If he hits, last guy takes damage from first guy. Last guy then displays himself. Then we increment who the next player is. We keep looping through until somebody dies. Okay? So what we were supposed to do for our homework, instead of just having this randomly out here, we're supposed to create a class for a fight where we can give it 2 players and tell those players to fight. All right, so we're going to move a lot of that logic in here. So we'll go up here. We're going to create I'll just create it below our dice class. We'll say class fight. And then we're going to def our initializer. And this guy will take in self, and it'll take in 2 players. So we'll call this player 1, player 2. Those are the 2 players that are going to fight, right? So we'll say self dot first guy is equal to player 1. Self dot last guy is equal to player 2. Now, one thing we can do is we can bring in some of our stuff from here, this initiative roll thing, and we can figure out who's going to go first. So we can say, so inside of our constructor, maybe we go ahead and we give ourselves our initiative roller. We decide who the roller is. We go ahead and put our 2 players into a list similar to what we have here. So instead of Blaine and Mike, it's players 1, players 2, something like that. And if we do it like that, we're actually going to store our 2 players as part of the object then. So if we do that, we could decide who goes first right here, or we can decide to do that when they actually fight. So we'll decide where we're going to put it in there. But for right now, let's just store the 2 players that are passed in inside of our list. Then we'll do a def fight. That will just take in a self. Inside here, we'll roll for our initiative. Well, actually, I'm just going to take all of our code from down here. And I'll paste it inside of fight, because that's what a single fight is, right? Single fight creates an initiative roller, which we could say belongs to the fight class, but we'll build it in here. We'll go ahead and roll it. We'll figure out who goes first. Well, we'll figure out who the current player index is. We'll give ourselves our attack roller. Then, now we're no longer going to say Mike and Blaine. Now we're going to say self.players at position 0 and self.players at position 1. Those are our 2 players, right? When we created our fight, we went ahead and we set a players list associated with this fight object equal to the list containing our 2 players that were passed in. So we no longer call them Mike and Blaine. They're now whatever 2 players were passed in. So I can pass any 2 players into the fight class and have a fight between those people. All right. So this is how we generically say whatever player is in the players list at bucket 0, whatever player is in the players list at bucket 1. While both of those guys are still alive, we'll set first guy equal to that, last guy equal to that. Similarly, when we go to display them, we won't say Mike and Blaine. We'll say players at bucket 0, players at bucket 1. Then we'll have our attack roller. We could also have said first guy, last guy here for the 2 people printing out. But then they would end up flip-flopping the order in which we showed them each time. Not the end of the world, but just have a little bit different output. The rest of these are all first guy, last guy displays. All right, so now that we have a fight class, we have our 2 players up here. I'm going to go ahead and delete all of that, and we'll say a fight is equal to a fight between Blaine and Mike, and then we'll say a fight dot fight. We'll take out a couple of lines in here just for spacing purposes. All right, so does that make sense? So now that we have all this stuff in here, if I kind of, one of the things that it lets you do is it lets you compress these classes down so you can kind of hide those details. Because remember, one of the goals of object-oriented programming when we originally talked about procedural versus object-oriented programming. We had the pile of wires here, which is procedural. And then we had the thing that actually looks like a telephone that we talked about as being the object. Well, even though we've written a whole bunch of code here, we have dice collections and we have players, all this stuff. If we start taking out some of these extra spaces in here, and we use the little thing to collapse the details in here, so we effectively put all those wires inside a little container, right? Now all of a sudden our entire program looks like this. That does all that stuff. I'll show you a little Linux thing here. So I'll say Python 3. Oh, sorry. Whether you're on, because I think Python, doesn't it give you a Unix thing on Windows if you're not using one of the IDEs? I think if you just download Python, it gives you like a Python command line thing, and it takes Unix commands like ls. So if you type in history in there, you'll see all the commands you've ever typed before. If you type in history, pipe, grep, let's see, I always type Python 3. It shows me all my Python 3 things that I've ever typed. Then if I just want to run this one command here, 634, let's say, I could just say bang 634, and that will try to run that. Let's see, players, oh, it's self.players. So I'll just go to fight. Remember, my players array is owned by this object, so this is self dot. Self dot. Hide that scary stuff again. All right, so there's our fight to the death. So that fight lasted forever. Why did that last so long?
Unless it kept rolling the armor class.
Yeah. But I mean, Mike's armor class was only a 6.
Still. Unlucky.
I mean, that was some really junky rolls you had
I guess
against.
so.
Against the bat.
I think the modifier is only 1 for attack, right? No, that's yours. How did I?
Yeah.
Wait a second.
You were just terrible. Whatever. All right, so do you see if we kind of pretend these guys, the whole idea is we're implementing objects up there. So if we put them in their plastic housing, like we're thinking about that telephone, do you see how all that detailed code we wrote now looks a whole lot cleaner? And this program does not look very difficult. We know that each of these objects has all those details inside of it. All those things are what's called encapsulated inside of those objects. So if let's make sure we have that that in our notes somewhere. Encapsulation. So we're going to generically call this hiding code within objects to simplify our program after the details have been written. It's not that that code doesn't exist. We can hit the little drop down arrow there and see all those details. In some other languages, and we could even do it with Python, we could actually put those classes in completely other files, separate files. But we're not doing things in here that are complex enough that we really need them in too many files, especially when Atom lets us just compress those things down. So it's convenient for us to have them all inside of one class there. But at the same time, we are gaining the benefit here of encapsulating all the stuff associated with players inside of that class. Same thing with dice collection. Same thing with dice. Same thing with fight. And then when we actually get down to our logic, and I'm pretty sure there's like a main program thing here. So it's like if name equal underscore underscore main underscore underscore, then do some stuff. Let me make sure this does what I think it does before I advertise it. Is it? Yeah. So let me kind of connect some dice here collect some. We're going to connect dice here. It's just, we're weird like that. This kind of looks weird, right? Especially this line right here, and we're like, well, why did you just throw this random extra crappy line in there when it kind of worked the same way before? That makes sense? And it really is to connect it back to something else, and it also is to support if we did have some stuff in other files that we brought in here. But let me kind of show you in a, let's do this in a Java example. So let me create a new file real quick. We'll call this guy hello.java, and I'm going to go ahead and say public class hello. So there's our simple hello world program in Java, which we'll be doing all next semester. So if I just run out and I compile this guy real quick, I'll say javac, which is the Java compiler, hello.java. It's happy with it. And I say java hello. There's my hello world. So it's running that program. Now, we see some similarities between these guys. So in our thing here, we have a whole bunch of things that say class. Here in Java, we have a class called hello. Just like over here, we have a class called player, a class called dice collection, a class called dice, a class called fight. Then inside of here, we have this guy called main. All right. Now, remember when we talked about our history of our programming languages? We had, what was the guy way at the very top? C. Then we went to C++. Then we went to Java and C#. Then we kind of had Objective-C over on the side. Then we had kind of Swift over here. That's kind of the programming languages that are the strongly typed ones. Then on the other side, we had our web languages, and Python is one of those. So let me show you hello.c. So this guy is from, let's call it the late 90s. So now let's look at the same thing. So we'll create a new file. Save this guy as hello.c. And I need to do an include standard io.h, int main, int argc, char pointer argv. I'm just going to leave it like that. All right, so that's hello world in C. So we'll go ahead and compile that guy. So gcc hello.c. Oh, it's because I put it on my desktop. I actually have to do a sudo gcc hello.c. So there's my hello world. So even Apple doesn't think you should be putting all this crap on your desktop. They protect the desktop. It's like, look, if you're doing crap out here and you're compiling and stuff, you need to give me super user privileges to do this. So that's why I had to do that little sudo thing. So if you're ever doing anything on a Linux or a Unix machine, which you will do during your 4 years here, this guy says execute the following command as super user. Super user do. Get it? All right. And then it says, okay, prove you're the super user. Give me your password, and then it says, look, you want to compile crap in your desktop, that's fine. All right, so in any case, in this guy up here, this is the Java compiler. And what does a compiler do again? Talked about there's two kinds of programming languages, compiled languages and interpreted languages, right? And compiled languages use a thing called a compiler. Interpreted languages use a thing called an interpreter. What does a compiler do? So you haven't memorized every word that's ever come out of my mouth? It's just liquid gold, people.
What does an interpreter do or an compiler?
I'll take either at this point. I want to know, what does a compiler do?
Doesn't that take the take what you've written and then turn it into readable instruction?
Okay, I mean,
For the computer.
that's probably at least a 70% answer. Not whole, I mean, that isn't like left field stuff. Go ahead. It's related to the strongly typed versus loosely typed. Most compiled languages also happen to be strongly typed languages. Most loosely typed languages also happen to be interpreted languages. Now you're looking at your notes.
I'm looking at Google's notes.
Go ahead.
It converts to machine level language prior to runtime.
Okay, from what to, you said to machine language from,
Yeah, from
That's right.
a high level language
Okay.
to a low language.
okay, that's the correct answer. High level language to a low level language. We have three kinds of languages, right? We have high level languages, low level languages, and machine language. What's machine language? Zeros and ones. We don't like that one, right? 2-button keyboard thing, that guy, right? Okay, what's a low level language? Man, we answered the zeros and ones so quickly. No, Python's a high level language.
Oh, assembly.
If you no C#, C, C++, all the languages that you will ever write in as a human are going to, well, not ever. 97.25% of the time when you write a language as a human, you'll be using a high level language. Low level languages, or what? How would you describe a low level language? It deals with the relationship with the CPU. Every line of code you write in a high level language translates into what?
Command.
How many commands on the CPU? What's our CPU? Think guy could do a bunch of magic tricks,
Yeah.
right? Remember that dude? Okay, so our CPU can do a zillion magic tricks, right? High level languages have a one-to-many relationship with the CPU. So every one line of code we write in a high level language like Python or something like that, a zillion things are happening. Remember we looked at Hello World in Linux early on? Right? And so when we write hello world in Python, we just say print hello world. You look at it Linux, it was this. And then we even talked about that we were using a power tool in there. We were using the syswrite system call, which some smart person wrote. That's probably hundreds and hundreds of lines of assembly code to make that thing work. So really you have, let's call it a 600-line program just to print hello world at the screen, if you were to see all the code involved.
It's little or no abstraction.
Little or no abstraction. For a low-level language?
Yeah.
I don't think that's an incorrect statement, but I wonder if you know what that means.
Well, abstraction is like it's trying to figure out how to put it into words. It's like
In 150, your abstraction example featured a picture of Einstein,
it's like
assuming they haven't changed the slide in 20 years.
minimization and how there would be none of that in the low language. Like I got the concept in my head, I just don't know how to put it into words.
Simplification.
Yeah.
So isn't it Einstein simplified on the stupid slide?
I don't think that was in there this time.
There's like a bunch of pictures of Einstein.
Yeah.
Yeah, I'm pretty. I don't think they changed that.
It's like,
I think at some point in time, Dr. Locklear had that thing just printed in blood, or something like that.
Little or no simplification. That's what I
Okay. Yeah. So A high-level language has a one-to-many relationship with the CPU. So we, as humans, we write one line of code that translates into a whole bunch of stuff on the CPU. It's a power tool. We like power tools. A low-level language has a one-to-one relationship with the CPU. We write something that looks kind of like English, but it's still only talking to the CPU in terms of one magic trick. Because CPUs have all these kind of magic tricks, but they're kind of indexed like binary number things. You know, call magic trick 00001001. Okay. We could look it up. We could have a manual somewhere and go and look up like, oh, I want this magic trick and I want this magic trick. But doable, but would drive you crazy pretty quickly, right? So we like a low-level language like assembler that isn't fun to code in. Well, I actually find it kind of fun to code in, but you're doing substantially less complex things. Like to do these assignments we've been writing recently, you find them hard in Python. You would drop out of school if you had to write them in assembly. It'd be thousands of lines.
Are we ever going to have to write in assembly?
Yeah, but you do
Right.
you do much smaller problems. Because when you're doing that, you're not learning about software development. You're actually learning about computer organization and architecture. After you compile a program, so we mentioned that compiling a program takes our high-level language, turns it into a low-level language. All right, so it does that conversion for us. We write 3 lines in high-level code. It converts it into 130 lines of low-level code so that we didn't have to write
Prior to runtime.
those 130 lines, right, prior to runtime.
Interpreter is during-
Then when we run it, those low-level codes get translated, get linked into the equivalent instructions on the actual CPU. Do magic trick this, do magic trick this, do magic trick this, that kind of stuff. Make sense? So these are all power tools in the middle. So we do it at the very high level. We abstract it all up to this point where we're using a language like Java or Python or C. And then when we compile it, or with Python we interpret it, it ultimately gets mapped into those individual instructions on the CPU so that we don't have to talk to the CPU on that one-to-one basis. It's possible, but it's not convenient. And it would strongly limit us on what we'd be able to write, right? Because, I mean, we'd introduce a whole lot of errors into our code. You just tell the CPU to jump once when it's supposed to duck. All of a sudden you get a very different solution to a problem, right? You know, especially if you're doing that, the schoolyard game where you're dodging rocks. They still play that?
Like Dodge Rock. Is that what you're talking about?
Well, I'm talking about dodgeball, but with rocks.
Yeah, Dodge Rock.
Do you guys have a name for it?
Yes.
See, I was mostly kidding, but that usually happens when you have kids in the neighborhood that aren't happy with each other and just start randomly throwing rocks. And then somebody always gets hit in the face, right? And all of a sudden the game comes to an end. And then they're all friends again. So you got to decide how to deal with the wrath of the parent of the kid who just got hit in the face with a rock. All right. All right, so we talked about compilers again. We're back on the same page with compilers and stuff. All right, so I just ran 2 compilers. I just compiled a Java program right here. This is the Java compiler. So here is my high-level code. When I was done writing that, if I do more hello.class, there's a file I created for me called hello.class. That is binary code, shown as a text file right now. All right, so that's what it created for me. That make sense? Well, it wouldn't look like that when you wrote it. This is just, it's a text. It's showing text on the screen, so it's trying to interpret what all those ones and zeros mean when they aren't meant to mean text. It's meant to be literally zeros and ones. It just isn't treating it as a binary file right now. If you wanted to read it correctly, you would look at what's called a hex editor. That would let you read it correctly. Okay. But unimportant, we see it's gobbledygook, right? What you'd see in the hex thing would be, it would look more zeros and onesy, but it'll still be gobbledygook to us in terms of just glancing at it and knowing what that guy's doing. Because it's calling a whole bunch of individual little instructions on the CPU. All right? So the compiler did all that hard work for us, so that all we had to do was call the Java virtual machine and tell it to run that program. Same thing. when I compiled the C program using GCC, that's the GNU C compiler. That's the open source C compiler. You can also use the original C compiler, which I assume is on here. Yeah, it is. Called CC, C compiler. That then creates, since I didn't give it any, you can give it a command line directive and say, name my executable this. The default one is something called a.out. So if I say more a.out, I get some similar looking crap. So this is the executable of my C program, imagined in Unicode instead of just the zeros and ones. If we were to look at this in a hex editor, it would look like zeros and ones. It would look like the hexadecimal version of the zeros and ones, but whatever. It would look less weird, but still look like gobbledygook. Okay? So, compiler, the C compiler is doing all that hard work for us. So that because remember, our C program just looked like this. I'm going to talk about these programs here in a second. All right, and then when we went to run it, we just ran our actual executables. Now, when I'm running, so my executable for C is just a file called a.out, which is a binary file. Why is it that I just run a.out directly here? In fact, here, let me, just to give you the real version of this, I'm going to call it... All right, so when I run my C program, now my program's called hello. Okay, I created my executable called hello. Why do I run my C program by just calling hello? And I call my Java program by saying Java hello. What's the difference between Java and C?
C's more of a low level, and Java's
Both are high-level languages. Go ahead.
Java not native to Mac.
Well, actually, Java comes pre-installed in the Mac, where Windows, you'd have to go and download it. But I would forget about the native aspect. You would have to do this exact same thing on a Windows machine. You'd still have to type in Java hello. So it has nothing to do with it being a Mac. It has something very specific to do with the nature of Java versus the nature of C. Why aren't we writing all of our video games in Java today? It's a really popular language. Tons and tons and tons of people like Java.
Does it hold the capabilities of languages?
Well, was that a question?
No.
Don't a lot of people.
That's a comment.
Yeah.
Because we definitely discussed this. Oh, you got something for me?
Don't a lot of people just use C++ and C#?
Oh, just cause?
Well, I mean, it's similar to Java, but
Well, Java's similar to them because Java came after them and is all based on C, right?
right.
I mean, even though these are two separate things, doesn't this and this look
Yeah.
similar?
It is.
There's a lot of,
I think it has more tools available as well for easier access.
Man, you would have thought that even just studying for the midterm, some of this stuff would have stuck. Just one of Java's kind of big features is the idea of platform independence. Write once, run anywhere. What does that mean? What does it mean to be able to write your Java program once and be able to run it anywhere?
You don't have to worry about different operating systems.
Okay, so I have this C program I just wrote, right? And I've compiled it. It's now an executable called hello. I can't take that over to a Windows machine and run it right now. I'd have to recompile it on Windows and hope I didn't have to change any little things. It's a simple enough program. I probably wouldn't have to do any more than just compile it again. But right now, it's compiled for specifically the system calls on Unix. Mac is a Unix-based operating system. Remember when we looked at Hello World for Linux? It was implemented using the operating system calls that are native to Linux. This is going to be written for the operating system calls that are native to the underlying Unix that Mac uses. On the Windows machine, the assembly code would use the underlying, whatever the equivalent of syswrite would be for Windows, for the operating system to know how to display stuff to the screen. So that means compiling the same C program on 3 different platforms, let's say, would produce different executables. So my little executable I wrote here will only run on a Mac. It might run on other Macs that have, are similar architecture to this one. So it might run on one that's up to 5 or 6 years old or something before you start running into, incompatibilities. But I can't just take that hello file, pop over to one of our Windows machines, and just execute it. Won't run. I'd have to recompile my hello.c file over on that machine. But my Java file, this hello.class file, when I run that, I run it using Java space hello, and it knows to look in the class file, and it will work. I can take that hello.class file. I don't need my source code anymore. I could just take that hello.class file onto a Windows machine and say Java space hello, and it'll run. I could take it onto a Linux machine, say Java space hello, it'll run. I don't have to recompile it. I don't even have to have the source code, because I already have the executable of it. Why is that? What is this guy? What is this Java guy here? Why do I have to say that instead of just calling the executable like I did with C?
Oh, is that because it's universal?
Well, it's the reason that I have to do this is because of the feature that it's universal. So what is Java doing to allow us to have platform independence, for us to write our code once on any machine and have it run on every machine that supports what?
Isn't it compiling and interpreting?
Java technically is kind of a hybrid language. It does. It compiles to a low-level language that runs on what? When we think of low-level languages, we think of them as running on the CPU.
Mm-hmm.
Java, the interpreting aspect of Java converts from one low-level language into another low-level language. It converts from Java object code into native assembly code for, in this case, Intel.
Okay.
So when I say this, what does that mean to you?
Nothing.
It means nothing to you?
I recall.
It's in our notes. It has to be in our notes.
I know I've seen it before. I just don't remember the definition.
Java virtual machine.
It's the Java virtual machine. What's a virtual machine?
Virtual.
It's another one of those buzzwords that probably means something easy, but it sounds real techy,
Probably.
that they should charge a lot of money for. That's why Sun Microsystems failed as a company. They never, we told this story too, they never monetized Java. They even had their stock ticker price. Their ticker symbol on the New York Stock Exchange was JAVA, was Java. Never made money off Java, ended up selling the company to Oracle. This is Java virtual machine. So then the question is what is a virtual machine? How many of you have ever used a virtual machine? Okay, what virtual machine have you used?
Linux and Windows Server.
Linux and Windows Server. Those are the operating systems you would have run on a virtual machine. What virtual machine did you use to run them?
VMware.
Okay, so you use something called VMware. Anybody else run a virtual machine before?
I think Knox.
The who?
Knox.
Knox?
Yeah.
NOx, like that?
Mm-hmm.
I don't know if I've heard of that one.
Android, like the Android OS.
Okay, so you can run Android OS on your computer?
Yeah.
Okay, fair enough.
I'm working with that.
Anything else?
Hyper-V.
Oh, I get it.
Parallels is another one if you're a Mac user. Parallels is a pretty popular one. Go ahead.
Just like an emulator?
Sort of. There's some of them that are implemented in terms of emulators. So an emulator mimics. I think the answer to your question is yes, based on the way you use the word emulator. So a virtual machine is a computer built, a computer's hardware built in software. All right, so what does this ultimately mean? Well, if you have a Mac and you want to, so one issue a lot of Mac users have is they might have a couple of Windows applications they want to be able to run on their computer, and instead of installing Windows on their Mac and then rebooting, so you're natively running Windows or natively running Mac every time, you might want to just be able to launch your one Windows application, your two Windows application conveniently from within Mac. So that's where a virtual machine comes in, where you would actually install either VMware, install Parallels, which, we'll use your word, emulates Intel-based hardware. Okay, you can decide. You have your system resources in your computer. I have a quad-core processor in here. I have 16 gigs of RAM. I have 512 gigabytes of hard drive space. I can say, well, I want 2 of my processors to be dedicated for my virtual machine. I want 4 gigabytes of my RAM to be dedicated for my virtual machine, and I want to set aside, 100 gigabytes of hard drive space for my virtual machine. So when I do that, all those resources now become owned by that virtual machine. So when that virtual machine starts, my Mac doesn't have access to two of its processors, 4 gigabytes of its RAM, and 100 gigabytes of its hard drive. Those are being used by that virtual machine. And what the virtual machine is doing is it is pretending to be your underlying hardware. So it's creating a layer that lives on top of your underlying hardware to fake it. So when your Windows program tries to run, it's running on a virtual processor that is Intel compatible. And then what the virtual machine does is it converts that from the Windows system calls to the correct underlying Mac system calls to run on the actual Mac operating system, doing that translation for you. From an end user's perspective, what do you get out of this? You run Windows inside of the Mac and run your Windows stuff. All the magic happens for you. But a virtual machine is a machine that is virtual. All right? It is creating your hardware in software. The Java virtual machine does the same thing. Instead of me writing my program to run on the Mac operating system running on Intel architecture, or writing my Java program to run on the Windows operating system running on top of Intel architecture, so on and so forth, I'm writing my Java program and then compiling it to run on the Java virtual machine architecture. So that means I can run my program on any computer that supports the Java virtual machine. Java virtual machine exists on the Mac. It exists on the Windows PC side. First, it exists on Linux, exists on Unix, so on and so forth. Okay, so it'll run on any machine that supports the Java virtual machine. That makes sense? Mm-hmm. I remember when we talked about this with C#, they mentioned that C# was platform independent. As in, C# is platform independent because it'll run on any machine that supports the .NET component architecture, which is the same thing as saying it's platform independent as long as you're running Windows. Go ahead.
So does that mean that if you run a application using Java, that no matter what, pretty much you won't be using your computer's full
100%.
Okay.
It's always going through that translation thing where the virtual machine is converting from the bytecode that was written for the Java fake processor into the equivalent native instructions for whatever computer and operating system you're on. So there will be a slowdown there, that conversion. That makes sense? I encourage you to go back and review some of those early notes. I would highly expect a quiz on Wednesday involving some of this stuff. So, yeah. In fact, I'm going to put a little quiz, virtual machine / old school stuff. So study up on that stuff. Think about some of the things we talked about today. It'll help you on the final anyways, but sounds like many of us have forgotten some of the earlier things. All right, I will see everybody on Wednesday.